All right, so welcome to Chapter 4. In Chapter 4, we're going to take a look at solving more of these, more linear programming. But what we're going to do is we're going to go beyond what we did in Chapter 3. We're going to go beyond two variables. Okay? So that graphical method that we looked at in Chapter 3 will no longer be sufficient because we're going to have too many variables. Right? We're going to take a look at something called the simplex method. Right? And that is going to be the approach that we're going to use to solve linear programming problems with more than two variables. You can use it for two variables too, just we've already done two variables with the graphical method, so we'll say, okay, this is the approach you would use. If you couldn't do the graphical method, which is anything beyond those two variables. Okay? All right, so we'll start with section 4.1, and in section 4.1, the first section of the part on the simplex method, we're going to lay out all the terminology, the language, and the approach for what we're going to do. Okay, we're going to take a look at what's called standard maximum form. We'll define what we are going to be calling our slack variables. We'll take a look at the simplex tableau, and we'll take a look at what it means to pivot. All right, so first off, in this section, we are going to start out by solving linear programming problems of standard maximum form. The simplex method, by definition, is a technique for solving linear programming problems, but it is necessary that those problems be in what's referred to as standard maximum form. So for this process to work, we have to be working with a standard maximum form problem. That is, the objective function is a function that needs to be maximized, so we'll only be doing maximization problems. The minimization problems are trickier, and they require a little tweak to the simplex method, so we'll take a look at that later. All of the variables have to be non-negative, so the non-negative conditions absolutely must apply, and all of the constraints have to be able to be written as this. Basically, the important part of that statement right there is that the inequalities have to be written as a less than or equal to form. Okay? So it's going to be things like this situation right here. Right? A farmer has 100 acres of land available on which he wishes to plant a mixture of potatoes, corns, and cabbages. So potatoes, corn, and cabbage. It costs money to produce an acre of potatoes, $300, and $260 for corn, and $180 for cabbage. He has a maximum of $20,000 to spend. Let's see. There are taxes of $5, $10, and $15 per acre on the potatoes, corn, and cabbage, and the farmer does not want to pay more than $900 in taxes. He makes profit off of selling his stuff, so $120 for potatoes, $40 for acre of corn, $60 for acre of cabbage. How many acres should they plant in order to maximize profits? Okay. So this is a standard maximization problem. So let's go ahead and just write it out. Now, one of the things that's going to happen here is when we talk about simplex method, we're going to talk about subscript variables. So we're going to have an x sub 1, an x sub 2, and in this case, we're going to have an x sub 3. This is going to be a 3-variable problem. My first variable is going to be the acres of potatoes. Second will be acres of corn. And my third x sub 3, is going to be acres of cabbage. Okay. And now that I've got my variables defined, I'm going to take a look at doing those other two things that I need to do simplex. I need to figure out what my objective function is, and I need to figure out what my constraints are. Right? Well, my objective function here is to maximize profits, so I'm going to write that as a profit equation. I make $120 for every acre of potatoes. I make $40, so plus $40 for every acre of corn, and I make $60 for every acre of cabbage. And so there's my objective function, and I want to maximize that objective function. Okay? Constraints. Okay? Constraints are our limiting things. Well, we only have 100 acres. So I know that however much I plant in terms of potatoes plus however much I plant in terms of corn plus however much I plant in terms of cabbage cannot exceed 100 acres. Okay. I also have a limitation on how much money I can spend to produce this stuff. Okay. It costs $300 per acre of corn or potatoes plus, what does he got here? $60 per acre of corn plus $180 per acre of cabbage, and I don't want to spend more than 20 grand. And I've also got a taxes issue here. I don't want to spend more than $900. So the $5 per acre of potatoes plus the $10 per acre of corn plus the $15 per acre of cabbage can't go on beyond the 900 I want to spend. And then of course I've got this, x sub 1, x sub 2, and x sub 3 all must be greater than or equal to 0. Right? My constraints are all of the proper form, that is, they are all less than or equal to's. My non-negative conditions apply, so this is a standard maximization problem. So now that I've got my constraints, I'm going to rewrite this as the form I need it to be in order to do something called the simplex method. Right? The first step in rewriting this as a simplex problem is to change all of those inequalities, all of these inequalities right here. We're going to change those into equals. We're going to change them into equality statements. So that first inequality is going to turn into this. X sub 1 plus x sub 2 plus x sub 3 plus s sub 1 is equal to 100. Okay. Now the variable that I'm adding is s sub 1. That is going to be our first slack variable. And what a slack variable does is the slack variable takes up any slack in the inequality. What I mean by that is, and for example, suppose that x sub 1 was 10, x sub 2 was 50, and x sub 3 was 30, meaning we planted 10 acres of potatoes, 50 acres of corn, and 30 acres of cabbage. Well, if you add that all up, that only adds up to 90 acres. So that would imply then that our S1, our slack, would be 10, or that we would have 10 acres that ended up not being planted. Right? Does that make sense? Right? I've got to turn an inequality into an equation. So I'm adding essentially an extra variable, and the purpose of that extra variable is to take up any potential inequality. Now, if the actual final answer works out so that it adds up perfectly to 100, then it just means that there is no slack for that first inequality, that there's no leftover unused, in this case, leftover unused acres. Right? When we write the slack variable for the second equation, or the second inequality, we're going to get this. 300x1 plus 60x2 plus 180x3 plus s2 equals 20,000. So now what that's saying is that slack 2, the second slack variable, will take up any extra money we have that we didn't spend raising crops. So I don't know what the final answer to this problem is, but if it works out that we have extra money that we didn't spend, that's what S2 or slack 2 would represent. Right? Now I think you see where this is going. How about that third inequality? Well, that would give us 5x1 plus 10x2 plus 15x3 plus s sub 3 is equal to 900. And now I've got a third slack variable, and that third slack variable, s sub 3, since it's in the taxes equation, would represent any money that we didn't spend on taxes. So I don't know what the final answer is going to be here, but if whatever that final answer is works out so that the taxes we spend on potatoes plus the taxes we spend on corn plus the taxes we spend on cabbage doesn't add up to 900 exactly, S3 would be that leftover money from the taxes, because we allotted 900, but ideally we'd like to spend less if possible. Okay. Now that I've got my inequality, my inequalities, wrong tool, written as equalities, now that I've rewritten my constraints, I can take my constraints and I can take my objective function and I can write something called the simplex tableau. And so our simplex tableau for this would look like this. The first row would be a, and I'm going to go to gray here, a 1, a 1, a 1, a 1, a 0, a 0, a 0, and a 100. The second row would be 300, and you can see that what I'm actually making here is I'm making a matrix. My third row would be 5, 10, 15, 0, 0, 1, 0. Oops, I made a mistake there. That should be the 20,000 from the second equation. And then this would be the 900. Right? Now I'm almost done. I need to add one more row. My next row is going to be negative 120, negative 40, negative 60, 0, 0, 0, 1, 0. And this matrix that we just created here is called our simplex tableau. Now I want to take a moment here to talk about where all these came from, right? So this green equation right here is my first row. So then that's the x coefficient, that's the y coefficient, or I'm sorry, the x sub 1 coefficient, the x sub 2 coefficient, the x sub 3 coefficient, the s sub 1 coefficient. This is the s sub 2, this is the s sub 3, and this is the z that came from that last one. Okay, so I'm just going to write those in really small above it so we can see what's going on. This is the x1, this is x2, this is x3, this is slack 1, this is slack 2, this is slack 3, this is z, and then over here we have our constants because that line right there is our equal sign. So then our second row here is our second equation, 300, I wanted the highlighter, not the arrow. 300x1, 60x2, 180x3, no s1s, 1 s2, no s3s, no z's equals 20,000. 5x1, 10x2, 15x3, no s1s, no s2s, 1 s3, no z's, 900. And the last row? Well, the last row is kind of hard to see, but if you take your objective function and take all three of these terms and move them to the left, they're all going to become negative. Negative 120x1, negative 40x2, negative 60x3, no s1s, no s2s, no s3s, 1z, and then it would be equal to 0. And that's our simplex tableau. And then we're going to use that matrix, which we're not calling a matrix, we're calling the simplex tableau because it's math, we have to make it complicated. We're going to use that to solve this linear programming problem by doing the following. We are going to, well, we've already done step 1, determine the objective function. Step 2, write the constraints. Step 3, add our slack variables. And step 4, by setting up the initial simplex tableau, the next thing we're going to do is we're going to do the process called pivoting. Okay? We're going to do that process by first locating the most negative indicator, that's the number in the last row, for the variable coefficients. Okay? If two numbers have the same negative value, then you choose the one that is further to the left. So this is going to be our most negative number. Then we are going to, and this is a typo, that says from, that really should say form. Okay, all right, so I went and fixed that file, so the one you have will be correct when you download it. Okay, so we form our necessary quotients. Now what a quotient is, it is the indicator constants divided by the indicator values to find the pivots. Okay. Constants are that last column. Values are the coefficients of the column above the indicator. That's the negative 120 that I just highlighted in pink. So I'm going to go back up to my tableau, and I'm going to make those quotients. So those quotients are going to be the 100 divided by 1, 20,000 divided by 300, and 900 divided by 5. Okay. So my first one is 100 divided by 1, or 100. The second one is 20,000 divided by 300. I'll see what that is. So bring up my calculator. 20,000 divided by 300 is 66 2/3. And then I got 900 divided by 5, which is well over 100 and some. So we're looking for the smallest non-negative value, so that's that. That means that 300 is going to be our pivot element. And so then what we're going to do is we are going to pivot, this is step 7 down here, we're going to pivot on that element. Now, pivot is just a fancy way of saying we are going to use row operations to change all other numbers in the pivot column to 0 by adding and subtracting. And then we are going to, once that's done, reduce that pivot number down to 1 by dividing. In this case, we would divide through by 300. If it had been the last row, we divide through by 5, those sorts of things. All right? Now, once we are done pivoting it, if all of the indicators, remember the indicators are the numbers in the bottom row, are now turned from negative to either 0 or positive, then we're done and we'll read the solution out of that final tableau. If it's not, then we'll find the next number we'll pivot on and pivot again. And then we'll find the next number to pivot on and pivot again. So basically this is an iterative process, which is a giant pain. It's hugely problematic to do correctly and to solve for. And so the reality is while you can't perform this process by hand, it's very difficult and time consuming. It's easily automated. It's a built-in function in Excel and Google Sheets. They build in this idea of performing linear programming problems. There's a ton of websites out there that can do it for you, and that's how we're actually going to do this. So my suggestion to you is that once we go beyond 2 variables, there is a by-hand technique. It's called the simplex method. Honestly, no one does the simplex method by hand. Right? It was developed and it can be done by hand, but it should not be done by hand. And so what we're going to do is we're going to use a website. Here is my suggestion. This is the website that I suggest. It's one called PHP Simplex. This is not the only website out there that works for linear programming, the simplex method. It is one that does work. Okay. The reason I like this one is I've tested it. It works on every browser that I've tested it on. It works on Windows, it works on Mac, it works on Chromebooks, it works on phones, it works on iPhones, Android, it doesn't matter. I've never found a format that it doesn't work on. It's kind of an ugly and clunky website, but I'm okay with that. Right? The way it works is you go to this click right here to start. You pick simplex, you tell it how many variables, in this case we have 3 variables, and how many constraints, in this case we have 3 constraints. Okay? We select that we want to do a maximization problem, and now this function line right here is our objective function. So these inputs in front of the x1, the x2, and the x3, it's asking for our coefficient inputs for our objective function. So I'm going to flip back over. Our objective function was 120, 40, 60. So 120, 40, and as you can see, I've done this before to make sure, 60, and then I've got my constraints down here. And so I'll go to my constraints. My first constraint was 1, 1, 1, had to be less than or equal to 100 acres we had to plant. Okay, remember that was these constraints are these ones right here. I'm not doing this because I don't need the slack variables and all that. The system will put those in for me. I just need my constraints. So my second constraint was the 300, the 60, the 180, and the 20,000. 300, 60, 180, 20,000. Now you may notice that there's drop-down menus right here where we could change from the less than or equal to a greater than or an equal sign, which means that there are techniques built in for doing other than the standard maximization problem. Back to here, third inequality was 5, 10, 15, 900. 5, 10, 15, less than or equal to 900. And then I'll click continue. Now, here it's talking about adding slack variables. For whatever reason, the authors of this website use X's rather than S's. S's are traditional, but it rewrites it as a standard maximization problem. Now, if you click continue here, it will step-by-step take you through. So if you click continue, it'll talk about building the simplex tableau. And if you continue, it'll march through pivoting as we go. Now, personally, I don't care about that. I don't need those intermittent steps. So I'm just going to click direct solution, and it chews on it for a second, and it tells me this. And it says that the best solution possible, and I can put it as fractions if I prefer. The best solution possible is to have our x1, our first variable, be 58 1/3, our x2 be 41 2/3, and our x3 be 0. So our x1 would be 58 1/3. Our x2 was, 41 2/3. And our x3 would be 0. Our z value, our maximization, would be, and then our z value, the maximum value of our objective function, what was that? That was 86,000? No, 8,600. 8,666 2/3. These were dollars, so that's kind of weird to think about dollars that way. Okay? And so there's our optimal solution. And what it did is it did this process right here, just computerized it. It wrote it as a program. And if you think about it, if you've ever done any programming before, this idea of identifying the quotients and picking the pivot element and then pivoting until all the indicators are positive or 0, it's just a loop. And so it'll loop through there and do it again and again and again and again and again. Right? So that's how we solve linear programming problems of multiple variables. There are some other things we have to take a look at, and we'll take a look at those in the next couple of videos, but I'm going to end this one here at 25 minutes, 24 and change. All right, see you back here for part 2.